Okay, so we're taking a look at trapezoids today. We're continuing to discuss polygons, and then more specifically, we're talking about quadrilaterals. And so we've talked a lot about parallelograms, and so now we want to talk about, well, what happens if all of the sides are not parallel? And that's what's happening here. In this case, the definition of a trapezoid is instead of both pairs of opposite sides being parallel, we're saying only one pair of opposite sides. Exactly one pair means we're actually implying by saying that the other pair of sides is not parallel, right? So in this case, if you take a look at the picture, the top and the bottom are marked as parallel, which means the other two sides are not parallel. So we have some vocabulary that goes along with this. When we're referring in a trapezoid to the parallel sides, we call those the bases of the trapezoid, right? So that in this case, if you notice, the top and the bottom are marked with the arrow, and they're also labeled with bases. Okay? The two sides that are not parallel, those are called the legs, right? And then we have ways of referring to the angles as well, and we refer to them in pairs. So when I'm talking about base angles, I'm going to say that the two angles that surround each base, we're going to group those together. So I'm going to say in this case, the bottom two sides, right, in the bottom corner here, okay, and in the bottom corner over here, that those would be a pair of base angles, right? And then in the top, I also have a different pair of base angles, right? We want to know about each of those pairs, okay? So trapezoids don't have a ton of special properties. Remember that these are parallel lines, and so they're going to inherit all of the things that deal with parallel lines. But specifically for trapezoids, we have to get into a little bit more detail and say, you know what, we're not going to just talk about a trapezoid, we're going to talk about a special kind of trapezoid. In this case, that special kind of trapezoid is called an isosceles trapezoid, right? So you've heard the word isosceles before, and it means the same thing here, right? When we learned about isosceles in the past, it was about isosceles triangles. When we talked about isosceles triangles, we were referring to two sides of a triangle being equal to each other. In this case, we're doing the same thing, but we're saying two sides of the trapezoid, and more specifically, the legs of the trapezoid. So those non-parallel sides, when they are equal to each other, we refer to this as an isosceles trapezoid. Okay? So isosceles trapezoids do have a couple of unique properties. So let's talk about what one of them is. If you have an isosceles trapezoid, then each pair of base angles is congruent. So remember when we talked about base angles, we said that those would be the ones that share a base. Right? So if I come down a little bit and take a look at this problem, I'm going to say, all right, so you're talking about an isosceles trapezoid, okay? And that means that the two legs, the two non-parallel sides are equal. Okay, that's what isosceles means. And that also means that the top and the bottom are parallel, just by the definition, like every trapezoid has that. Okay, so what this theorem is saying is, if it's an isosceles trapezoid, which means it looks like this, that the two angles along each of the parallel sides will be equal to each other. So I can say that this bottom angle and this bottom angle will be equal to each other. And I can do the same thing up top. I can say this one is equal to this one. Okay. The top and the bottom, not necessarily equal. In fact, they won't be equal to each other, right? But definitely the two angles that share a base, which we call a pair of base angles, will be congruent to each other, okay? So if we put this into application, we'll see a problem that looks like this. So what they're doing here is they're giving us an isosceles trapezoid, which even if they didn't state it up here by saying is an isosceles trapezoid, they've marked it for us on the picture, right? We see parallel lines top and bottom, and we see congruent legs, right? DC and EF are equal to each other. So even if they didn't specifically state it, we know that for sure. In addition, in this one, they're giving us the measure of one of the angles. They're saying angle C is 65 degrees. And they're claiming that we should be able to find all of the rest of the angles. Okay? So let's start off by using the property that we just talked about. That theorem said in an isosceles trapezoid, pairs of base angles are equal to each other. So if I'm going to say this 65 is paired up with angle F because they share that parallel line CF, right? One of the two parallel lines. So I'm going to say if this is 65 in an isosceles trapezoid, this one is also 65. So now the question becomes, how do I go from the bottom pieces to the top pieces? And in this case, we're not even going to talk about trapezoids or trapezoids or isosceles anything or special theorems. We're going to go back to what happens when I'm just talking about parallel lines in general. So if I just had parallel line, and I had a transversal going through them, what we know about these is that angles that are same side interior angles like these two, okay, are always going to be supplementary to each other, right? So we're going to say these two angles should be supplementary. So in this case, that's really what I have. I have parallel lines and a transversal. And so if this is 65, this is going to be, angle D is going to be supplementary with 65, which in this case, that looks like 115 degrees. Okay, 115 plus 65 gives me 180. And if you notice, I can confirm that angle E is also 115 two different ways, right? I can say it is supplementary with angle F, or I could say it's equal to angle D, which is its base angle, right? So this is actually kind of where the proof of this comes from. If I asked you to prove this theorem, we can use the fact that parallel lines with same side interior angles are always supplementary, and use that to prove that the base angles end up being equal as well, right? So I'm asking you a quick question down here, and the question is, if this was not an isosceles triangle, can we determine anything about the angles? Do we know anything? Like if I just gave you that 65, what would we know? So let's just really quickly consider that, and I'm going to draw myself an additional trapezoid to help us out with labeling. Okay, so here's my new trapezoid, and I'm going to assume that this one, we don't know that this one is isosceles. So what we definitely know is that the top and the bottom are still parallel. That's true of all trapezoids. So if I put a 65 right here, and I asked, can we fill in any of these three angles? Do we know anything? What we do still know, what's still true, is that this one that is along the same transversal is still supplementary with it, okay? But I don't know anything about these ones over here, right? Because this 65 does not necessarily show up on the other base angle because it's not isosceles, which means I don't know anything about this one either. So I can't necessarily say how the rest of the 360 is split up between these, but I do still know that same side interior angles are supplementary. That's true of all trapezoids all the time because it has that set of parallel lines, okay? So we can still fill in some information if it's not isosceles, but we definitely can't fill in everything without some more information, okay? So let's take a look at the other important property of trapezoids, and that is that the diagonals in an isosceles trapezoid, again, we have to be very specific, this only works for isosceles trapezoids, they will be congruent as well. So again, diagonals would be when I connect vertices through the middle of the shape. So if I go from bottom left to top right angle, and I do it the other way around, right, I'm claiming that those two lines that I just drew, assuming this is an isosceles trapezoid, that they are congruent. So again, here's what my picture will look like. I know that these lines are congruent. I know the top is parallel to the bottom. Right, those are my bases, and I know that the legs will be congruent to each other. Right, so again, if I asked you to prove this, it looks like I could probably use some properties of parallel lines and some triangles, and I could prove to you that the diagonals are congruent. But this is really what the property is saying. If I were to measure this line, I would get the same thing as the one right next to it. Okay, so let's talk about the last property, and that is the midsegment of a trapezoid. So here's what a midsegment of a trapezoid is. Right, we've heard this word midsegment before. It showed up when we talked about triangles and we had midsegments of triangles. The definition is exactly the same. Okay? The midsegment of a trapezoid is when we connect together the midpoints of the two legs of that trapezoid. So again, taking a look at my picture here, if I wanted to draw a midsegment, I'm going to put a midpoint on each of my legs. So I got one over here and one on the other side. Okay? And again, when I draw a midpoint, what ends up happening is that these two pieces are equal and these two pieces are equal, but not necessarily the same. Like the left side and the right side are not necessarily the same length because this is not isosceles. They didn't specify that, right? And to draw the midsegment, I'm going to connect those two midpoints together. So I'm going to go from one midpoint straight across, connect to the other midpoint, and I've drawn myself a midsegment. And so there's some properties about this midsegment that are true. Here's the first one. The midsegment is parallel to the bases. So remember, in a trapezoid, the top and the bottom are already parallel. That's the definition. And so I'm adding to this and I'm saying the midsegment, this new line that we just drew, is also parallel to the other ones. Okay? The second property is a little bit stranger. It's going to take a little bit more work to figure out. What this one is saying is that if you find the average, okay, of the base, the top base and the bottom base, if you find the average of them, which is what half the sum of the lengths would do, right? If I add up the sum of the lengths and cut it in half, I'm really just finding the average. If I take the average of the top base and the bottom base, I should get this middle one. So let's just do like a number example, and then we'll take a look at an algebra one as well. If I know that this top base is worth 5 and this bottom base is 11 units long, and I asked you to find me the length of the midsegment, what you would do is you would say, let's do 11 plus 5. That is the sum of the lengths of the bases, right? And then I would cut it in half, which is the same as dividing by 2. So I'm going to say in this case, 11 plus 5 is 16. 16 divided by 2 is 8. I know that this midsegment is 8 units long, right? So we can gather a lot of information about this midsegment and about some of the angles that are created by it, just knowing that the midsegment is parallel to the bases and knowing that it is basically it's the average of the bases, right? So let's do one algebra-related problem that uses this fact. Okay, so if I give you this problem, they've given me, well, they've stated that QR is a midsegment, so we know that these properties apply, and so they're telling us that LM, which is a base, is 4x minus 10, and Pn on the bottom is 8, and that is also a base. So what we said is if you add together, okay, the bases, which is 4x minus 10 plus 8, and you divide that by 2, that you should get the midsegment, which they're telling us is x plus 2. Okay, so I have to solve this. So I'm going to do 2 steps worth of work at the same time. I'm going to multiply the 2 over to the right hand side and make it 2x plus 4. Okay, and then I'm going to combine the pieces on the right. Negative 10 plus 8 is negative 2, so this is really 4x minus 2. Okay, and then I got a pretty easy solve. I'm going to subtract 2x over. I'm going to add the 2 back to the right and get a 6, and I find out that x is equal to 3. Okay, so I'm claiming that if you plug in a 3 here, you notice I got a 5, and if I plug in a 3 here, it looks like I get 20 minus 10, right? 20 minus 10 being, 12 minus 10, which is 2, right? If you take the average, okay, of 8 and 2, that you will get a 5, right? So that's really all this property is saying.